Hello, I am Mrs. A.A Nadagouda, lecturer, Department of Chemistry, KLS Bogte PU College of Commerce and Science, Belagavi. We are in continuation with unit number 4, Chemical Kinetics, and this is third video. Up till now, we have studied the rate of a reaction, how it is written for how it is written in the form of differential rate equation, then what is rate law and how the order can be determined by using the rate law equation. We have also seen what is the unit of rate constant for the different order reaction, and even we have studied the order can be 0, it can be a fraction, or it can be a whole number, right? So today we are going to study another property of reaction, that is molecularity, which helps in understanding the mechanism of the reaction. Whenever we write the equation for any reaction, we balance it, right? Means theoretically, by seeing the reactant and product, we are balancing the number of molecules on both sides. So the number which we are writing on the reactant side shows that how many species are taking part in the reaction. That is, how many species are colliding simultaneously to bring out that reaction. And this is nothing but the molecularity of the reaction. Okay, that is the number of reacting species. It may be atoms, ions, or molecules taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction. So, molecularity of a reaction is always a whole number. Now, here are some examples of unimolecular, bimolecular, and trimolecular reactions. So, first example is NH4NO2, that is ammonium nitrite, in which only one reactant is there and giving two or more products. Such type of reaction is called as decomposition reaction. Now, as it includes only one reactant molecule, it is unimolecular reaction, means molecularity is 1. Bimolecular reaction, that is 2HI, gives H2 plus I2. So here, two molecules of HI are reacting, means colliding. Therefore, it is bimolecular. Bi means 2. Trimolecular or termolecular, in which three reactants are taking part. Okay, 2 NO and 1 O2. Okay. Now, more than this, that is more than 3 molecules can collide simultaneously. This probability is very small, and such reactions are very rare, and these proceed with very slow rate. Okay, so in such reaction where the number of molecules are more than 3, which step is determining the rate of reaction? That can be answered by going through the reaction mechanism. Okay, so we can write it as rate determining step. Now the complex reactions involving more than 3 molecules. Such reactions are taking place in more than one step. Means there are different elementary reactions. Out of that, only one reaction is going with very slow rate or slow speed, right? And this reaction is called as rate determining step. So here is one example given in which the 10 molecules are reacting. The order may be 10 theoretically, but practically or experimentally, order of this reaction is second order reaction. Here, whenever the number of molecules are more, such reactions are taking place in different steps. It's just like relay race, is it? In relay race, how we can predict which team will win the and so that can be determined or that can be predicted by the slowest runner, is it? So by knowing the speed of slowest runner, we can identify or we can recognize. Like that, in complex reaction, the slowest step determines the rate of reaction, means predicts the rate of reaction. So from all these concepts, that is order and molecularity, we can find out there is a difference. So this difference is given and it can be asked for 2 to 3 marks. So first point should be written as definition. Okay, already we have seen the definition of order and molecularity. Then the second point is order is experimentally determined, whereas molecularity is theoretically calculated. Order of reaction can be 0 and or fraction or whole number, but whereas molecularity cannot be 0, it is always a whole number. So order can be derived from rate equation, whereas molecularity can be given or derived by mechanism of the reaction. Now, one more example of rate determining step is given on page number 102, that is decomposition of hydrogen peroxide. If you want detailed information, you can go through this example. Okay. So, whatever we have predicted, that is especially order, it is from differential rate equation. But every time it is not possible to get the differential rate equation or instantaneous rate for a reaction, because we have to draw a graph, then we have to uh, draw the tangent to that graph, and then at particular point we have to find out the rate of reaction. So it is tedious work, and hence to avoid this difficulty, we can find out the integrated rate equation, and this integrated rate equation is different for different order reaction. So let us study the integrated rate equation for zero order reaction and first order reaction. Okay, now this question is asked for 4 mark or 3 mark. So what is mean by zero order reaction? The order of a reaction is 0, means it is independent of concentration of the reactant. Okay, the rate of reaction is proportional to 0th power of concentration of reactant. So to derive this, we have to consider a reaction. R is giving P, means R is reactant and P is product. Okay, so according to rate equation, it can be given as rate is equal to minus dr by dt. Why minus sign? Because we are considering the rate of reaction with respect to reactant. Okay, we are considering the rate with respect to the reactant, and hence we have to take it as negative sign. Okay, it is given as K is into R raised to 0, where square bracket R is molar concentration of reactant. Okay, raised to 0, anything raised to 0 is considered as what? Unity. Okay, therefore this value comes as 1 and rate is equal to minus dr. Now changing rearranging the terms, taking dt on this side, opposite side of the equal to sign, we can write the equation as dr is equal to minus k into dt. Integrating the equation on both sides. So integration of d of r is equal to, minus sign should be out of the integration sign, k into dt. So d of r, integration of derivative is nothing but that term, that is react r, concentration of r is equal to dt is t, integration of dt is nothing but t, that is minus kt plus I. Whenever we are taking the integration or we are integrating the equation, we must take a constant, and that is called as constant of integration. So here I is called as integration constant. Okay. Now to find out the value of I, we have to take t is equal to 0. So at t is equal to 0 means initially concentration of R is taken as R0 or R0. Okay, that is called as initial concentration of the reactant. Now substituting this value in equation 1, R0 is equal to minus K into T is equal to 0 plus I, which gives I is equal to R0. Again substituting this I value in equation number 1, we'll get R is equal to minus KT plus R0. Okay. Now comparing this equation, with y is equal to mx plus c, which is the equation of a straight line, right? So m gives the slope of the reaction, slope of the graph, c is the intercept on y-axis, and x and y are coordinates. Okay, so from this is y, this term is y r, then this term is mx, and this term is c. Okay, so minus, now the graph is plotted of r, concentration of reactant, versus time, means r will come on y-axis and t will come on x-axis. So remaining is minus k is nothing but what? Slope, and r naught will come as intercept. Okay, then the equation can be given as k is equal to r naught, bringing this r naught on opposite side, it will come as minus, or we can take this minus kt on this side, so it will become plus, and this r will bring it on this side. Okay, so r naught minus r divided by t is nothing but what? K, and this is called as integrated rate equation for zero order reaction. Okay, so here the derivation is completed. Now let us see how is the graph plotted. Okay, so this is the graph which shows the variation in concentration versus time for zero order reaction. Now if you see this graph, concentration of R is taken on y-axis, that is nothing but R, then this is t, time t, and then comparing with y is equal to mx plus c, m is nothing but what? Minus k, that is slope, and c is intercept, that is this r naught value. So c intercept is given as this part. Okay, so here are, now these zero order reactions are very rare or uncommon, and the examples are some enzyme catalyzed reactions or reactions which occur on metal surface. I have given the two examples of this. Let us study the integrated rate equation for first order reaction. Similar type of derivation is there, only some changes are there in this. So what is first order reaction is, the rate of reaction is proportional to the first power of concentration of reactant R. Okay, again we have to consider the same reaction. R gives P, but here you have to write is a first order reaction. Okay, then rate is equal to minus dr by dt is equal to K into R raised to 1. When we are writing this R initially, when in rate equation, okay, we have to write raised to 1, okay, or raised to 0, remember. And then we are taking initial concentration, that time we should take R0 or R0, that to be taken as subscript. Okay, so rate is equal to anything raised to 1 is nothing but the same quantity, right? So rearranging the terms, taking R terms one side, so this term will take one side, this R we will bring it here, and this dt will bring it here. Okay, so dr by R is equal to minus K into dt. Okay, integrating on both sides again, integration of this quantity, right, and integration of K dt separately. So this is whenever dr by R is there, it will come as ln R. Ln is nothing but what? Log to the base e, which is also called as ln. Okay, so ln of R is equal to minus kt plus I. Again, I is integration constant. So to find out the value of I, we will take t is equal to 0. So R is equal to R naught. Okay, now when you are showing such symbols or square bracket R naught, remember it should be written like this only. Okay, not like this. Sometimes students are writing like this, which is wrong. Okay, so the 0 should be out of the bracket. Then substituting the value in equation number 1, ln R naught is equal to minus K into 0 plus I. This gives ln R naught is equal to I. Again substituting the value of I in equation number 1, ln R minus Kt plus ln R naught. Again rearranging the equation. How we will rearrange? We will take this ln, this Kt on opposite side, so it will become plus Kt. Okay, and we will bring this ln R on this side. Okay, so this will become minus, and hence we can write the equation like this in this form. Or else if we bring this ln R naught on the opposite side, if we bring this ln R naught on opposite side, it will become minus is equal to minus Kt, right? So ln R minus R naught is nothing but what? Ln R upon R naught is equal to minus Kt. Cancelling the minus sign on both sides, and we will reverse the term. So K is equal to 1 upon T into ln R naught upon R. We can write this equation here also. Just see, Kt is equal to, not with minus sign, sorry, Kt is equal to ln R naught minus R minus ln R. That is nothing but Kt is equal to ln R upon, sorry, R naught upon R. Okay. So to convert ln to log, we have to multiply by 2.303, and that is nothing but k is equal to 2.303 divided by t into log of R naught upon R, right? So this is the another form of integrated rate equation of first order reaction. Okay, so this question out of any one integrated rate equation can be asked for 3 to 4 marks. Now let us see how the graph is plotted. The graph can be plotted by using ln R, or we can take it as log of R naught upon R versus time. In both cases, the slope is given as k minus k and intercept is given as ln r naught. Okay. Or here, slope is given as k upon 2.303. Okay. So these are the two different forms of graph for first order reaction. Then these are the examples. Hydrogenation of ethene to form ethane. Okay. Or else all natural and artificial radioactive decay of unstable nuclei, that is radioactive reactions follows first order reaction. Okay, so here are some examples for first order reaction, and today we will stop it here only. Thank you.